Hello again. So in this part of this chapter, we are going to deal with bivariate descriptive analysis. So we have already mentioned that bivariate analysis is analyzing the sample data when each member of the sample is examined for two separate variables or attributes. So let's just say we have multiple university students as the parent population, and we have just collected a random sample of n students from this parent population. And in the first row of this table, we have recorded the weights of the students, and in the second row, we have recorded their heights. Or similarly, let's just say we have randomly selected n second-hand automobiles, and in the first row, we have recorded their second-hand prices, and in the second row we have recorded their odometer values, so the distance that they have traveled so far. So in this case, if such a table or such a sample data is to be analyzed, we need to use bivariate descriptive analysis methods because our objective here should be discovering the relationship between the first variable and the second variable. Okay, it is possible that because these two variables, they are observed on the same member of the sample, they may be dependent on each other. For example, larger the height of a student, larger the weight of the same student as well. Therefore, or in the other example, if the odometer value is large, then the second-hand price of the automobiles are expected to be smaller. So our objective here is to discover the relationships between these variables, and then it may be possible to predict the other one based on the observation on the previous one. For example, you can observe the odometer value of an automobile, and based on that odometer value, you can predict the second-hand price by using the statistical relationship between these two variables. Okay. However, our objective here at this point is not this. Our objective is to understand the sample data only, because descriptive analysis deals with this problem only. All right, so how can we analyze a bivariate data using descriptive analysis techniques? The basic methodology is to draw a scatterplot diagram. It is sometimes referred to as the scatter graph. It's a type of mathematical diagram which uses Cartesian coordinates to display values for two variables for a set of data. So it is basically easy. We have two variables. The first variable set is denoted with X, and the second variable set denoted with Y. Of course, the size of these two sets should be the same because they are collected over the same sample with size n. And on the horizontal axis, we are going to plot the X variable, and on the vertical axis, we are going to plot the Y variable. If the plotted points, if this scattered points over the two-dimensional space, they form a pattern, or they form a significant behavior that shows a pattern. In that case, we can say that there is a certain relationship between these two variables. Now, we need to see this in this following example. Let's just say we have observed 10 candidates on their smoking habits, and the number of packs that they have consumed is recorded through a year. Okay, so for 12 months, we have recorded how many packages of cigarettes that they have consumed, and we take the monthly average of these values, and we have seen that the first member of the sample has consumed 66 packages of cigarettes per month in the year. So this is the monthly average of the cigarette consumption in packages. The second member has consumed 97 packages. The third member consumed 16 packages, so on and so forth. So this is the monthly average. And for the same year as well, we also have collected the number of visits to hospital for each member of the sample. So the first member of the sample has visited the hospital 9 times in this previous year. So we have collected 2 things about the previous year for each member of the sample. How many packages of cigarettes that they have consumed on the average, on the monthly average, and how many times that they have visited the hospital in the last year. Now, our objective here is this: is there a relationship between these 2 variables? Can we say that the more the consumed the cigarettes increases the number of visits? Is it possible? So it is only possible to state a hypothesis about this to draw a scatter plot diagram such as this. So over the horizontal axis, we see the number of packages of cigarettes that these member of the sample have consumed, and on the vertical axis, we observe the number of visits to hospital for these members. So let's just check the first member. The first member has consumed 66 packages of cigarettes per month on the average, and there has been 9 visits to hospital, and we see that value as 66 and 9 here as a Cartesian product or as a vector plotted on this 2-dimensional space. Just like that, there are 10 observations in our sample, and for all of them, we indicate the scatter plot. For example, for the 9th member of the sample, we have 15 to 3 as the variables, observed variables. So we see we have 15 here and 3 here, as you can see. 15 to 3 is here. A similar observation has been made also, which is 16 to 3. Okay, so we have 16 to 3 and 15 to 3 for the 3rd and the 9th members. So they are very close to each other. Now, what is the final comment after drawing this scatter plot diagram? Obviously, you see that as the number of packages of cigarette consumption on monthly average increases, the number of visits to hospital in that year also increases as well. Therefore, you see there is a increasing trend in this plot diagram just by observing 10 observations. But still, let me tell you that the final comments that you can make can be more strong if you have a larger sample size. Okay, with such a small sample size of 10 observations, just by drawing a scatter plot diagram will not be enough to put a strong hypothesis about the relationship between these 2 variables. But for practical purposes here, for example purposes, we are trying to give a small sized example. Therefore, we had a sample of size 10. All right, another way where we can discover the dependence between variables is the contingency tables, or it is sometimes called cross tabulation. They are being used mostly for discretized data, okay, not for continuous data, because if we have a continuous data, such as in the previous example, we can draw a scatter plot to discover the dependence structures between 2 variables. However, if we have a discrete data, in that case, we can use contingency tables. For example, in the first example here, we have a sample of 100 people. 100 people. Some of them are male and some of them are female. 47 of them are male and 53 of them are female, and 12 of them are left-handed and 88 of them are right-handed. Now, by looking at these values in the cells, we can see the number of left-handed male people, number of left-handed female people, number of right-handed male people, and number of right-handed female people in this population of 100. Now, our objective here is to indicate if there is a relationship being between left or right-handed and the gender of the person. Okay. Now, how can we discover this relationship by looking at this data? Now, you see, we have a 2 times 2 matrix here, and as you can see, the rows of this matrix are not dependent on each other. For example, we have a ratio between the male and the female people in left-handed people, 4:8. So you see over 12 left-handed people, only 1/3 of them are male and 2/3 of them are female, whereas for the right-handed people, half of them are male and half of them are female. So we should say that it is much more likely for a female person to be left-handed compared to be a male person according to this data. Of course, I mean, this is just a made-up table. I mean, you should not believe in what I am saying here. This is just a made-up table which explains how the cross tabulation or the contingency tables works. Now, in the second example, we have 150 observations in our sample. Again, we are observing 150 people. 52 of them are smokers and 98 of them are non-smokers. And 50 of them have an IQ level that less than 100, according to an IQ test. 71 of them have an IQ level between 100 and 150, and 29 of them have an IQ level which is greater than 150. So how can we see if there is a relationship between the smoking habit and the IQ levels of a person? Again, we are checking the ratio between the IQ levels are, you see, 18 to 25 to 9. So almost these ratios are similar to 2, 3, and 1. Okay. So the IQ levels among the smoker people, the number of people who has an IQ level greater than 150 is almost half of the number of people who have an IQ level less than 100. And so the proportion between this value and this value is 2 to 3 approximately. A similar situation can be observed within the non-smoker population. Again, the ratios are very similar to 2, 3, and 1. Even if there are small differences, we can say that the behavior of these values are very similar in the smoker and the non-smoker population. Therefore, we can say that the IQ levels of any person is not related to the smoking habit. It is not dependent on the smoking habit. Again, I'm saying that this is just a made-up table. It may not be true. We need to check solid studies about this. Okay, this is just a made-up data. All right. Of course, instead of these descriptive statistics, which are given in the figurative form, in the form of a graphical representation or in the form of a table, we can also create mathematical the statistics in the form of mathematical functions, such as the sample covariance and the sample correlation. Okay, in univariate descriptive analysis, remember the mean, median, mode, and sample variance and sample standard deviation. These were statistics given in the mathematical function form. And we can also discover the relationships between two variables observed on the same member of the sample by calculating the sample covariance. So again, please imagine you have such a table where we have observed n observations in our sample, and for each observation we have collected two variables, and our objective is to discover if there is a relationship between these two or not. Now, the sample covariance, it is an estimator of the covariance between two variables in the parent population. So basically, by using the sample covariance calculated through our sample, our objective is to predict the covariance between the variables in the parent population. Okay, we would like to generalize this information for the parent population. So sample covariance is formulated like this. The calculation, the way we calculate the sample covariance is very similar to the theoretical covariance. Remember, what is the definition of the theoretical covariance? It was the expected value of the deviation of the first random variable from its mean times the deviation of the second random variable from its mean. So in order to statistically estimate this theoretical covariance, what we are going to do is, first we need to calculate the sample average for two variables, x bar and y bar, and we subtract the sample average of x's from the x variable of each member, and we subtract the average of y values from the y value of each member, and we multiply these two values for each member, and over all members we sum up these product of two deviations. So this is the first deviation of the first variable, this is the deviation of the second variable, and this is the product of two deviations, and we sum this product of two deviations over each observation. Then the summation is divided to n-1, just like in the sample variance formula. Because we do not know the true means of the parent population and we are using the sample means, we need to divide this summation to n-1 in order to estimate an unbiased covariance. So this is the expanded form of the previous summation. But let me tell you that sample covariance just indicates the type of the relationship between two variables. So depending on whether the covariance is positive or negative, we can say that there may be a positive or negative covariance between these two variables. However, we cannot just say it by looking at the number, okay? The strength of the relationship can only be determined by the sample correlation, okay? So the next step is to learn sample correlation. And in order to calculate the sample correlation, we definitely need to calculate the sample covariance. It is therefore we are teaching it first. Now, let's practice the sample covariance formulation in this example. This is a small size example again. It is not a good idea to work with such small sample sizes, but we are giving this example for practicing purposes. Okay, our objective is to calculate the sample covariance in a very easy manner in this application. And it says that we have randomly selected 4 automobiles of the same brand and the model, and these are second-hand automobiles. The odometer values and the second-hand prices are tabulated here. So the odometer values in thousands of kilometers are given as 17, 12, 16, and 20 for these 4 automobiles, and their second-hand prices are respectively $21, $25, $22, and $19,000. Now, how do we calculate the sample covariance? The first thing that we need to do is to calculate the respective sample means for x values and y values, which are respectively 16.25 and 21.75. Then we apply the sample covariance formula, which means for each member of the sample, we subtract the mean of x values from the x value and the mean of y values from the y value and multiply these two deviations. So this is just for the first member. As you can see, this is for the fourth member, 20 minus x bar and times 19 times y bar. And we sum up the product of these deviations and divide it to n-1, which is 3 for our sample size, and the covariance here is minus 8.25. Now, we should say that there seems to be a negative relationship between these two variables. So as one of them increases, the other one tends to decrease, or vice versa. However, we cannot make any comment on the strength of this relationship by looking at this number. So we need to check sample correlation. Okay, but please do not forget, still, even if the correlation will indicate, it is going to indicate that there's a strong or weak relationship, it is not to make it is not a good idea to make a strict comment with such a small sample size. Okay, remember, small sample sizes are not good ideas. Now, how the sample correlation is calculated? The sample correlation is the ratio between the sample covariance and the product of the sample standard deviation. So first we need to calculate the sample covariance and write it in the numerator, and in the denominator we calculate the sample variances, multiply them, and then take the square root of them to convert them in the product of the sample standard deviations. Now you see, because we have n-1 in the denominator part of both the numerator and the denominator, they can cancel out. So we can say that there's a easier way of calculating the sample correlation, which is the sum of the product of two deviations divided by, in the square root, the sum of squared deviations for the first variable times the sum of squared deviations for the second variable. So whichever you use. Now here we should say that if the sample correlation, just like the theoretical correlation, the sample correlation can only take values between -1 and 1. If the sample correlation is close to 0, we should say that there is either a weak or no dependence relationship between two variables, linear dependence relationships, of course. Okay, no linear dependence relationship between these two variables. And if the sample correlation is close to 1, then we can say that there may be a positive linear dependence between the variables in the parent population as well. And if the sample correlation is very close to -1, then there seems to be a negative linear dependence relationship between the two variables in the parent population. Now let's calculate the sample correlation for this example. We have already calculated the sample covariance, so all we need to do is to calculate the sample standard deviation for X and sample standard deviation for Y. And for that, we can calculate the sample variances and take the square root of them. Now, explicitly, how we calculate it is not given in the solution, but you can practice this by looking at the formulas given in the univariate descriptive analysis. As you can see, the sample variance formula is here and the sample standard deviation is here. So you can practice these values by using these formulas. Then, by dividing the sample covariance to the product of the sample standard deviations, you will get a correlation which is very close to -1. Now, such a correlation would have indicated that there is a strong negative relationship between the two variables. As one of them increases, the other one tends to decrease. However, remember, our sample size is very small to reach to this strict conclusion. Okay, even though this value is very close to -1, we should say that there may be a possible negative linear relationship between these two variables. However, to make such a comment with such a small sample size is not a good idea. Okay, so we can increase our sample size. We can, for example, check 100 automobiles instead of 4 automobiles, and based on the results obtained from there, we can make a much strong conclusion. All right, so this is just going to be the end of the video lecture for this presentation file. In the rest of the presentation file, we are given an empirical proof of the central limit theorem. We have already mentioned quite deal of theory, and we have solved many questions about the central limit theorem. In fact, we have given many examples of YouTube videos where the central limit theorem is explained. So this empirical proof is just another explanation of the central limit theorem, how it works. As the sample size increases, the central tendency of the mean tends to be the normally distributed variable. So that explains this. You can read it by yourselves. And the reading assignment for this chapter is given in this last slide. Please perform your reading assignments as well. So this is just going to be end of this video.